Welcome everybody to the preseminar. Today we have the honor to have Richard Stanley giving a talk, and he's going to start with some background material. All yours, Richard.
Okay, yeah, so thank you for the invitation. I'll begin with sort of three topics that will be useful when I get to the main material. First, let's consider Pascal's triangle, and I'll just discuss some aspects of it which I want to find analogs or generalizations of. So, of course, this triangle is familiar to everyone, and my indexing is always that these arrays begin with row 0, and the entries in the nth row begin with the 0th entry. So, of course, in Pascal's triangle, the kth entry in row n is just the binomial coefficient n choose k. And a lot of properties of this triangle are easy to understand because we have this nice explicit formula for n choose k. We have a generating function for the entries in row n, the sum over k, n choose k, x to the k. Of course, this is just the binomial theorem, 1 plus x to the n. So I'll be looking at some analogs of this. We can ask for the sums of powers of the entries in row n. For instance, the sum of the squares, sum of n choose k squared, sum over all k is 2n choose n. 2n choose n, well, it's not the nicest possible function, which for me would mean that the generating function would be a rational function, quotient of two polynomials. But this should say, I left out a backslash, but it is algebraic. It does satisfy a polynomial equation with whose coefficients of polynomial on x. On the other hand, the sum of the cubes of the entries in row k is not even algebraic, and there's no nice formula for this. So we can compare this sort of bad behavior of Pascal's triangle with a couple of the triangles I'll be looking at in my main talk. We can represent the recurrence defining Pascal's triangle by a poset, or if you don't like posets, you can just think of it as a diagram. The points in the diagram correspond to the numbers in Pascal's triangle. I've labeled them, by the entries in Pascal's triangle. Every point is connected to the two above that, which add together to give that number. So this is just a way of representing the recurrence relation satisfied by Pascal's triangle. And we can characterize this poset by saying that, it has a top element, which, well, actually, I think of it as the bottom element of the poset. I'm drawing it as a poset. This is drawn sort of back or upside down because I want it to look like Pascal's triangle. So it's characterized by saying that every point lies directly above 2 points. That is, in poset language, is covered by 2 points. It's planar. And every time you see one of these lambdas, a point covered by 2 points, it extends to a diamond. So these properties characterize this poset, which is just a direct product of chains, the non-negative integer, 2 copies of the non-negative integers. Moreover, we could say that, again, the recurrence relation that defines Pascal's triangle is saying that each label is the sum of those on the level above it that are connected by an edge. And as a consequence, these labels, like this number 6, is the number of paths, or if you want, saturated chains from this element to the top. Because the number of saturated chains satisfies the same recurrence relation. Every path from here to the top either goes through this point, and there's 3 saturated chains through here, or this point, 3 through here. So we get the same recurrence. Good for binomial coefficients. This is well known, how they're counted by certain lattice paths. Okay, so we'll see some analogs of this. The second topic I wanted to quickly review for those who don't know it is the connection between rational generating functions and linear recurrences with constant coefficients. So this, blackboard bold n denotes the set of non-negative integers. And if we have a function from n to the complex numbers, then it's a basic theorem in enumerative combinatorics that the following 2 conditions are equivalent. F of n satisfies a linear recurrence relation with constant coefficients, a1 up to ad, for all n greater than or equal to 0. And equivalently, the generating function for f of n is a rational function. It's a quotient of 2 polynomials, and the denominator is essentially, well, given by the coefficients of the recurrence. The numerator is a p of x. If this recurrence holds for all n greater than or equal to 0, then the degree of the numerator will be less than the degree of the denominator, that is less than d, and that depends on the initial conditions. We could note that if we have a rational generating function whose degree of the numerator is greater than or equal to the degree of the denominator, that just means that the recurrence holds not for all n greater than or equal to 0, but for n sufficiently large, namely the degree of p minus d plus 1. A standard example of a rational generating function would be the Fibonacci numbers. They satisfy the recurrence that fn plus 2 is the sum of fn plus 1 plus fn. And the initial conditions, f0 is 0, f1 is 1. The generating function is then x over 1 minus x squared. Okay, so that's my second of my 3 background topics, and my last one will be a quick word about free monoids. So a monoid M is a set with an associative binary operation in an identity element. So it's just like a group, except we don't insist on inverses. We'll say that M, a monoid M, is freely generated by some subset G of M if every element of M can be uniquely written as a product of elements in G, well, allowing repetitions. And then we'll say that M is a free monoid. For example, now sometimes, it's not so clear whether a monoid is free or not. If we look at the set of all finite sequences of A's and B's, so you could say I'm looking at words in the alphabet A and B, with an even number of B's, and the monoid operation is concatenation or juxtaposition of words. The identity element would be the empty word. So the condition is every word has an even number of B's. Is this a free monoid? So it takes a little bit of thought to see that, yes, it is free. It's freely generated. Well, the set of generator it's freely generated by an infinite set. It's an infinite number of free generators. A, BB, BAB, BAAB, etc. BAAAB. A B followed by a bunch of A's followed by a B together with A. So any word that has an even number of B's can be uniquely written as a product of these generators. Well, we're going to be interested in the number, well, first, yeah, we're going to be looking at graded monoids where the words have, the elements of the monoid have a certain degree or length. So we'll say M is graded if it's a disjoint union of sets M0, M1, M2, etc., or any element in Mi times something in Mj lies in Mi plus j. So if the monoid just consists of words, and a subset of words in some alphabet, then the length of the word would be a grading. You know, we could let all words of length n be M sub n. So we're going to be interested in a certain situation where we want the number of words of length n, or in other words, the cardinality of M sub I. So if each of these M sub i's is finite, let's look at the generating function. It's like a Hilbert function, which tells how fast the monoid grows. The coefficient of x to the I will be the number of words of length I. If M is freely generated by script G, then we'll let G of x be the generating function for the lengths of the generator. So it's the sum over all I, the number of generators of length I times x to the I. Well, if monoids are freely generated, then there's a very nice way to go from the number of generators to the total number of words of length I. Namely, G of x to the nth power is going to count the number of words of length n. You could write the first factor G of x, you choose some word in G, script G, then the next factor, you choose another word, etc. So like G of x squared is going to count those words which are products of two generators. So we sum this up over all n greater than or equal to 0, and we'll get the generating function for f of x, 1 over 1 minus g of x. Very common situation in enumeration that a generating function has a form 1 minus some other generating function, and there should be some free monoid lurking in the background there. So like going back to the previous example, where M was finite words in the alphabet A, B with an even number of B's, graded by the length of the word. The free generators were this set. There's one generator of every positive length. So G of x is x plus x squared plus x cubed, etc. That's x over 1 minus x. So f of x is 1 over 1 minus g of x. So 1 over 1 minus x divided by 1 minus x, which is 1 minus x over 1 minus 2x. That's 1 plus the sum of 2 to the n minus 1, x to the n. And indeed, the number of words in 2 letters of length n with an even number of b's is 2 to the n minus 1. When n is greater than or equal to 1, and is 1 when n is 0, the empty word. And finally, just an example of a monoid that's not free. You might wonder if there's a simple example of that. Let's let M be all finite words in the alphabet A, B, except for the word B. Obviously, this is still closed under multiplication, under concatenation of words. But it's not free because ABA has 2 factorizations, AB times A and A times AB. Neither of these factors, can be factored further because B is not in the monoid. Okay, that is my background talk. Are there any questions?
So
Pranab, do you want to unmute yourself and ask the question directly?
Yeah. So I noticed that in the given example, the set of strings with even B's is like a regular language, so we can represent it with a regular expression.
Right.
So my question is, would all languages that are representable by regular expressions, are they all monoids?
Yes. Well, practically by definition, I mean, yes. It's practically the definition of a language is the same as a monoid. Yeah, there's a discussion of this in chapter 6 of my book, Enumerative Combinatorics, Volume 2. Yeah, and these, I mean, it's exactly right. The reason we got this, well, not, well, there's a stronger result than a rational generating function for the number of words of length n. If you look at the actual sum of all the words, as a non-commutative power series, then that is a rational non-commutative series. And that's equivalent to being a regular language. And that's part of the theory of regular languages.
I think that makes sense.
So getting this rational generating function for the number of words of length n suggests that the language is regular, but it's not, it's a weaker condition.
Okay. Thank you.
Are there any other questions? So we thank Richard again for the preseminar.